Okay, we're going to continue the lecture to cover the topics for perspective projection. This is under MEKH 5453 Industrial Machine Vision. Okay, let's talk. We are going to look at what we're going to talk about on these particular topics. Okay, um, briefly, we are going to talk about how we are going to understand about the geometric transformations from the 3D world area. Then we are going to simplify it to the 2D, the projections to 2D in camera. Then we are going to learn about two types of distortion and the process of the calibrations. All right. Okay, let's just look at this very general image here. So we are going to learn about the just a very simple camera, the pinhole camera. All right. So if you imagine yourself using a camera, right? So whatever outside from the camera is considered a 3D world where you can see a 3D object over there, right? For this example, we can see a tree over here. Then this tree is going to be mapped to the 2D image on the sensor inside the camera through the pinhole here, and then this is related to the camera parameters. Okay, so the question is very simple. How we can represent a projections from 3D world to 2D image coordinate. So it means that how we can calculate from this 3D object come out later in the camera on the sensor plane. So where is the coordinate is up to the parameters and the formula we're going to learn after this. Okay. So the representation is very general like this. So you have the image for 2D here. All right, so this is a 2D here. You can just write, if you see this is a format, this is also the same one. So this is your UV related to the point for the X and Y at the sensor at the back here. And then you have the P is here. P is consists of the parameter for the intrinsic parameter and the extrinsic parameter. So you have two components here. One is K and one is RT is the other parts of the parameter. Then this is going to be your coordinates for the 3D world. So because of the 3D, so you must have the X, Y, Z, and this is for the homogeneous coordinate. So you have all these coordinate with the parameters, then you can come up with the final results for the U and V, which is the points on the sensor. So basically in this particular slides, we're going to learn how to have coordinates from the world coordinates denoted by xw normally, then transfer to camera coordinates at the center here, and then finally you can get the image coordinate on the sensor plane. So there are three areas you can find out, you can understand, you need to understand how you can come up with this number to the end over here. Okay, let's look at the formula again. So in a pinhole camera model, right, the perspective projections is governed by the following transformation. So that's why last time we learned about the transformations of the image, right? We are going to use more on the matrix calculations. So again, this is the same formula just now. So we are going to define this one. This xv is equivalent to the 2D image coordinates of the projection. Then you have the x, y, z are the 3D world coordinates of a point. So you have to remember that this is for the homogeneous coordinates. Remember that. So this is 3D, this is 2D. So after this one completed, then you're going to map it on the 2D images. So K is the intrinsic camera, right? This is the parameter for the focal length and the principal point. All right. Then you have the R and T. So R and T is the extrinsic matrix. This is outside from the camera. So it describes the camera positions and orientation. And the last one, the third coordinate, which is this one, is used for homogeneous normalizations. Then, so let's dive down on the camera matrix just now. So this is the camera matrix at the P. So what is actually K and RT? So P is equivalent to K and RT. This is both in matrix transformations. So you have the 3D world just now here, and then you have the 2D on the image plane. So in between that, you have the pinhole camera, right? So that will be considered or known as the camera coordinates here, denoted by XC, YC, and ZC. This is the original world coordinate. Normally it's denoted by XW or capital XYZ, and then later you have the pixel coordinates here, which is on the sensor X and Y. So in between the world coordinates and the camera coordinates, right, you are going to use the extrinsic parameter, which is the RT. And then after that, you have the finally you get the XC, YC, and ZC. You are going to transform it again to the 2D by using the intrinsic parameters. So let's just look what is K and what is RT. So K is just like this. It's a fx. This is the this is fxxy, and this is cxcy. This is q, something like that. So this is just the positions in the matrix for this formula. We're going to dive down later and explain what is K inside here and the RT over here. So R, you can see that this is the locations of R. Okay, and then this is for the translation. Remember that translation is the one over here and the rotation is over here. All right, so let's proceed. Okay, let's look at the first one, the extrinsic parameter. Okay, so the extrinsic parameter represents the locations of the camera in the 3D scene, or representing a rigid transformation from 3D world coordinate system to the 3D camera's coordinate. The parameters are camera position, which is the translation, and angle of rotation in space in relation to fixed object. So this is the camera coordinates. You can see that C is for the camera, and then you still have here, this is the R and T, because this is a line, because this is going to be a homogeneous. So from the world to the camera, you still have the 3 x, y, z over here until you can get the intrinsic parameter. You can get the x, y only. So this is the arrangements on the value for the translations and the rotations here. Okay, so the translation metrics last time we had learned in the translations are the image transformation. So that is going to be using the same formula. Okay, so we are going to look here. So world coordinates to camera coordinates. Okay, to go from the world coordinates to camera coordinates, from the world to camera coordinates, you have to apply a rotation and translation, usually written as R and T. So this is going to be the formula, which is R is a 3 by 3 rotation matrix, T is 3 by 1 transition vector, and this is for the world coordinates, and this is for the C coordinates. So by using RT, the transformations for the rotations and translation, basically what we are going to do is we are going to change the value from the coordinates for the world to the camera coordinates here at the pinhole. And last time in the class, we learned about the rotations, only one formula, because we learned last time is only by 2D only. So you have X and Y, right? This is X and Y. And what we learned last time is we only going to rotate like this. So this is basically rotate around the z axis, right? So you have the z here, so you are rotating this at y, and so we are going to use this one. So if the rotation is based on the rotation around y axis here, so this is rotation, so you're going to use this particular formula. Whereas if you are going to rotate around the x-axis, then you have this particular formula. So the rotation axis is giving you different formula. Okay, because last time we only learned in 2D rotation. So right now for the camera, of course, this is a 3D world, so you can do some translation on each of the axis X, Y, and Z. Right? So let's just understand a bit on the example. Okay, so for the extrinsic parameter, so we just look at the questions here. A camera is placed at the world coordinate 532 and rotated 45 degree about the y-axis. So this is y-axis. The camera is at world coordinate, so this is the world coordinate 532, this one. So the translation vector is, so we are going to learn about one. We need to find out this is a 45 degree. So translation vector at y-axis means that y-axis is here, cos theta, sin theta, negative sin theta, cos theta. So we're going to use 45 degree here. So get all the informations and calculate based on the cos, sin cos this one, and then you can finally get the rotation is this value 0.7, 0.7, 0.10, 0.7, 0.7. So this is the rotation matrix, and the translation vector is which one? Translation vector is given 532 here. Okay, so this is given. So of course you can put all the informations on the R over here, 3 by 3, and 3 by 1 is for the translation vector. Finally you can get the parameter for the extrinsic R and T like this. So this is the answer. So let's move on. Next one is the parameter for the intrinsic part. So the intrinsic parameter represent the optical center, so related more on the camera, which is the inside the camera. Okay, it represents the optical center and focal length of the camera or a projective transformations from 3D camera's coordinate into the 2D image coordinates. So we have the camera coordinates 3D go to 2D image coordinate. So the parameters are focal length, optical center, and lens distortion coefficient. These parameters are essential stereo calibration and structure from motion. So this will be the formula just now, same one like we learned at the beginning here, here, right? So this is K. So what is Fx and for Fy? So Fx and Fy is the focal length along x-axis in pixels on the sensor camera. Fy also is the focal length along y-axis in pixels. So S is for the skew coefficient, which is normally 0. Okay. So Cx and Cy is the x coordinate of the principal point. This is the point at the center of the sensor for x and y. Okay. All right. So this is going to be used to calculate where is the locations of the map of the 3D point from outside till the sensor. Okay, example. Now we are going to understand the intrinsic parameter. So a camera has the following properties. So you are given fx 1000, fy 980. You have the principal point cx 650 and cy equivalent to 480. Skew factor is 0. So put this one and construct the intrinsic matrix K for this camera. So the intrinsic pattern is this one, K is equivalent to this one. And of course, this is the one that you are going to put in the matrix itself. Okay, so this is the answer. Okay, another example. Question. So this is a camera has a horizontal field of view, which is the FOV X is equal to 60. Vertical field of view FOV Y is equal to 45 degree. This is image width 640 pixels, and image height is 480 pixels. So assume no skew and the principal point is exactly at the center of the image. So what that means is for the principal point is basically this is your sensor, right? So this is X. Oh, so this is Y, this is X. So the principal point is over here at the center. So you just like divide by 2 for both of the width and length. So assume no skew, and this one, calculate the intrinsic parameter fx and fy in pixel given formula f is equivalent to w over, this is over 2, divide by tangent fov divided by 2. So you can put the values over here, fov for x, right? Fov for y, you have 60, 45. So this is the equivalence from the formula, apply. So you have W here. Okay, so this is 640 divided by 2. This is also H. This is related to the center principal point, right? So tangent 30 is because of divide by 2, this one. So you come up with the calculations. Finally, you can get the final answer is 554 pixels, and the Fy is 580 pixels. Then after you have all these informations, right, you basically can map the image from the camera coordinates to pixels on the sensor itself. Okay, once you have a camera coordinates, you apply the intrinsic k. So this is we're going to learn about the k matrix k to map to the pixel coordinates on the sensor. So of course on the sensor we have only 2D x and y. So what we need to do is the process that we have to normalize the camera coordinates just now. So for example, just now it is this one. So you have the xy here, xy 1, right? So this is x c y c z c and 1. To normalize for this one, you have to divide xc divide by zc, and then you have yc divided by zc. So this is equivalent normalized for this one. This is for this one. So we don't have z anymore because we are using it for the normalizations. Right? Z divided by z is equivalent to 1. So it's the same one. Then after that, you have to apply the K matrix, which is the intrinsic parameter. So finally, you can calculate the value of the U and V, and then that will be the final answer, where from the 3D world, then you go to the camera coordinates, and finally, you are going to get the UV value on the sensors. Okay, let's look at questions. So camera parameters for the intrinsic, right? It's an example. A 3D point is given in camera coordinates. This is camera coordinate xc, yc, zc. The camera has the following intrinsic matrix K is given like this. So we need to find the final value for UV. So we have to do the same process again like this. You have to normalize first and then apply the matrix K. So normalize the point by dividing by ZC to get coordinates in the normalized image plane, right? Then apply the intrinsic matrix K to find the pixel coordinates. So based on this one, you have to divide 0.4 divided by 2, 0.5 divided by 2. You can get the x and y here, right? So this is the normalizations. And then after that, you have to calculate, this is x and y, right? So you have to calculate with the k intrinsic matrix. And finally, you can get the u and v here from the calculations, which is the final coordinates in the example is u is equivalent to 122, comma v is 400. So that will be the locations on the sensor at the back for the 2D images. Okay, so to make it short, so this is what are the parameters of the formula related from the 3D world to the 2D image on the sensor itself. So this is the formula that you're going to use for the particular conversions on the 3D world to the 2D on the image. So this is just a simplifications on this one, right? So it's the same thing, just to make it in one page. So for the next page is normally I put more an example of the calculations. So you can read the questions and understand one by one, which is the same thing. We have to understand the concept of projections from the 3D world to the 2D. So these will be the calculations. So this is given the what I call the details on the solutions of the questions. So you may just need to look at that again, and there will be few questions here, especially on the exercise. They only have answers for you to try. So this is going to be example again. So this is the calculations on that. All right. So um, just to cut short for this topic, we just need to understand what is the main point or how we can do some projections from the 3D world, okay, from the 3D world to 2D world. Okay. So look at the example and try yourself on the exercise itself. Right. Thank you very much.